for the electron in the box. Of course, it's a 3D box, so the fundamental state is not degenerate, as we know from elementary quantum mechanics, and I write the wave function as a dimension of, as a function of A, the width of the box. The first excited state is a threefold degeneracy, depending on X, Y, and Z, and this is a Z state associated to this first excited state, and you have the same wave function for the different state, as you know, and this is the wave function and the other wave function. Okay? And now the transition energy, very simple calculation, depends on A square, and if I remember experimentally, the dependence was not exactly A square, but minus 8.85. So not far, not very far from that. Now there is a big difference in the first term. If I plot the energy the absorption associated to the transition between n equal 1 to n equal 2, 1, 1, 2 here, and 6, 8 on the other side, so there's a factor of 2 almost of difference, okay? So we can say a little bit that actually the cube is not really, has not the dimension of the lattice parameter, but something a little bit larger, since the 6 metallic cation can attract the electrons that are trapped in the vacancy, so the dimension, the actual dimension of the box that keeps the electron is somehow larger, a little bit larger than the width of the box. And so if we do that, somehow, that's a correction that can be introduced in our simple model, a Thorne model, and the alpha, this correction, is perfectly reasonable. We say that something like 10% difference of in the width, in the estimate of the effective length of the box will induce, will reproduce the dependence. What is important is actually that it goes almost as expected when we change the A parameter as A minus 2. Okay, now this is for absorption, but it was found also that those color centers can exhibit luminescence. Luminescence means that you absorb light and you re-emit light, okay? What was found is that the emission peak of the emission spectrum occurs with a shift toward larger wavelengths, and this is called the Stokes shift. And this is something happening for all emitters, the absorption in the solid state. All emitters will have an absorption band and a luminescence band that are shifted by this Stokes shift in wavelengths, occurring at higher wavelengths or smaller energies. And how can we understand that? The effect is actually induced by the interaction between the lattice and the electron trapped in the center. There were experiments done in the 60s on those centers to compare the absorption spectrum and the luminescence spectrum. So sometimes people speak either of luminescence or fluorescence. It's the same. Fluorescence will be more for chemists, for molecules, dye molecules. Luminescence more for solid state systems, condensed matter systems. And so now the idea is how can we explain this Stokes shift, which can also be seen in the spectrum of the NV center. The absorption of the NV minus center, for instance, is in the green, and the emission is in the red. So large spectral difference between the two spectra. And it's exactly what you see here. There's a frequency difference, a wavelength difference of almost a factor of 2 between the absorption and the other one. So I want to understand that, and somehow that will, for that, the explanation is what's called the Young-Taylor effect. So the Young-Taylor effect is something a little bit mysterious that was proposed in 1937. It's like a general rule. It tells you that if I take a molecule, it was found for molecular system, and this molecule has, usually the molecules has a lot of symmetries in it. And this symmetry, as we'll see later for the specific case of the NV centers, will induce degenerate states, a strong degeneracy in the system. And so what you can show is that if now I distort the molecule, then the symmetry is reduced, lower, And this geometrical distortion of the molecule actually may lead to energies that are smaller. So somehow very symmetrical systems will have its own energy, but if I change a little bit the system by breaking somehow all the symmetry it has, at one point, this will lead to lower energy. And somehow it's the Jahn-Teller distortion effect. If you take a system, the system, at least for the excited state, will go to lower energy by breaking its symmetry. So now we can consider that, for instance, illustrate that with the toy model that we have for the F center, for the electron trapped in these crystals, in these alkali crystals. Instead of considering the cube here of lattice parameter A0, we now distort the system. We now considered a rectangular shape and a parameter which is somehow we elongate in what we keep one distance constant. We keep the volume constant, but we extend the system in one direction. Okay? So that means that somehow you have here C, and B on the other side. Okay? I don't know if the symmetry will be like that, or if somehow it will be like that, or it will be like that. No one can tell me. So somehow the Jahn-Teller effect does not predict the direction of the distortion. Just tell you, if you go to this kind of structure, you should find energy levels that have smaller, that are at lower energies compared to the energy level that you can compute in this system. So we will gonna check that. And
what exactly is driving the Jahn-Teller distortion? Well, I know that carbon is not a Jahn-Teller. You need a Jahn-Teller ion.
it just the fact that somehow the nature won't like that. So you will go to just thermal interaction will bring you to a system with this lower energy. I will try to explain that. Perhaps you wait a little bit, and maybe the answer will come, or partially, and then we can discuss the point that you highlighted. But it's important. Yes, you're right. Somehow, nothing in that tells you how it can occur. Tell you that there is something that can lead to energy state having lower energy than the one of the full symmetry of the system. So I consider this kind of distortion. So I take my box, and now I stretch it, okay, keeping the volume constant. And it's not difficult calculation to introduce this distortion parameter eta on the calculation to compute now all the energy levels once we have, compare it without and with distortion. So you do this calculation, and you have the different kind of things. Of course, what you will find is that the distortion will partially remove the degeneracy. It will remove the degeneracy for the axis for the energy level that are along Z compared to the two other ones, while X and Y play similar role, of course. So we will have a partial removal of the degeneracy of the system for the excited state. So now I plot here the energy as a function of the distortion parameter. And there are two different curves. The first curve that we have here, this one, this is for the ground state. What we see is that the minimum here is obtained for eta equal 1. For the ground state, the lowest energy that can be achieved is for the highest symmetry, the cube. Okay? If now I consider the two other systems, this is for that energy. So now I consider the first excited level. Okay? And now what I see is that I have completely different behavior. For instance, for the wave function that are mostly along the X or Y axis, okay, I see here a different value, eta. Okay? And if now I consider the other branch for the Z state, so the other system, it's obtained for this value of eta. So we have different behavior for the excited state. If I consider the E prime to Z, this is minimal for eta equal to, and the value is indeed lower than the one we have without distortion, with the cube. If I consider the other system, I reach another value for eta equal square root of 2 over 5. Again, it's a toy model, nothing to understand in this value, just to understand a little bit how it works. And then we get this value for the minimum value, which is also smaller than 2. So it's the illustration about the fact that if we have this stretching of the box, we can lower the first energy level. Sorry? Sorry? No, we'll see after. We try to compare at the end with the experiment. Okay, so this is the situation here now. So again, they are associated to different stretching, so we don't know how it's going to be. But this is in the excited level. Remind that the excited level will only survive for a given time. And this is important for the following. So I have now this energy system with this transition, okay? And this can be excited, for instance, by this dipole, okay? So I can address a different situation by just changing the polarization of the excitation light. And this is the energy diagram that I can obtain for eta equal 1. So what we have done here is to compute the potential that induce actually the quantization of the vibrational modes of the electron in the box. So somehow we have this box. The box confines the electrons, but due to the phonon, for instance, the box can vibrate, okay? And those will induce vibrational modes of the electron trapped in the box. So now all this calculation, the Jahn-Teller calculation, can be really done explicitly using ab initio calculation. This is really something quite remarkable. We have now methods by building an n-electron wave function where we can really see that. So all this works very simple because we have very simple geometry of the system, but there's no problem now, at least for talented people, to reproduce all these ideas, all these calculations, now for realistic systems. This can be done. But now, okay, now we can understand where the Stokes shift comes from. So we have these, what we have computed up to now with the model is the electronic potential as a function of the eta parameter, the stretching parameter here, okay? And basically, it's those curves. I take the minima that I have here. Sorry, I should put it here. Okay, I suppose the minima that I have here. And I see that they do not occur for the same eta. Okay? So we start from the ground state, the electron, and to get the lowest energy, it's the cube geometry. Okay? Now what we have, it's an absorption. So the photon goes to the excited state by absorption. But this is done within a time that the box cannot distort. Okay, so we have, this is the Frank-Condon principle. It tells you that you have transition that keep the symmetry of the system. So the symmetry of the system is kept and goes to the same starting from the parameter eta equal 1. So here we have the cube. Here we have a cube. Okay? But now the cube here, it's not the stable emission, depending on the transition we have. Okay? It will relax to a parameter eta, which is higher, for instance. So it will have, now we have something which is like that. I don't know how this occurs, but somehow the geometry has changed. Okay? And the geometry has changed now. The emission now, and this is done through a non-radiative decay process. This is not a radiative transition. This is a non-radiative decay. Just the box that is changed due to the interaction with the phonon somehow, or the lattice interaction that creates this distortion so that the energy is lower. Now what I will do is I have again the emission of the phonon. Okay, this excited state cannot survive for a long time. There is a radiative decay. So within, for instance, a few nanoseconds, it will emit a photon toward the ground electronic level. But again, Franck-Condon principle tells us that this decay will occur with the same geometry of the box. So I end here. I have the same geometry. And now, this is not the stable geometry for the ground state. So then there will be a relaxation, again by interaction with the lattice, okay, coming back to the first situation. And I can do that scheme very efficiently a lot of time. But that tells me that when I do the calculation, I see that the photons that are emitted on the emission wavelengths of the luminescence is completely different than the emission for the absorption, that the wavelength for the absorption. There's a shift. That's a Stokes shift. And I can do now the calculation. I have everything. I can just evaluate the energy difference between here and here, for instance. So I have everything. I have all my potential here. Okay? I know exactly. I've done the calculation. So this is the value. I need to take the value for eta equal 1. Okay? I know, so that tells us this value. When I do the calculation, I found this. Okay, and now I can also do the other calculation for that. Eta equal 2. So this is a relaxed, so somehow the stretch situation, which I found more stable in energy, corresponding to lower energy. And in that case, I can also calculate the transition from here to here. I just need to stay to determine this value. This gives us the distortion of the box, the right value, and now I can do it here. Okay? And I can compare the two differences, and I see that the emission wavelengths or the emission energy is 0.4 times the absorption energy. And when I compare now the two values, well, I am not far from that. It's 0.48 instead of 0.4. And that's real data. So I have a very simple model, as you say, but which somehow explain all the main figures of the physics happening. And that's general. So in all our systems, basically, we will have an initial configuration which has a high symmetry of the system. Then when we go absorption, transfer the system to the excited state, then it gets quickly distorted. After non-radiative decay, which is the emission of the photons, its energy decreases to a new energy, but again, this energy now will relax will come back to the ground state by interaction with the lattice. And I have this four-level scheme that you might know, that we can have. Here, absorption, non-radiative decay, emission, and non-radiative decay toward the ground state. And it's a four-level system that you found, for instance, for dye molecules and a lot of ions in solids, or that are used, for instance, for all kinds of solid-state laser. They rely on those systems. And the explanation is this one. Okay, the physics is this one. Now I have done almost all the things. So what I need is to keep now, what I would like is to have those ideas in mind. Of course, they are limited in this. They are limited to this very simple system. And now to see how these general ideas somehow applies to the specific case of the NV centers. And for that, somehow what you see is that, of course, you can have absorption and emission in the structure in the potential well associated to the ground state and to energy level, but then depending also on the harmonic oscillator that is quantized associated to all the substate, the sublevels inside this main electronic potential. And somehow what you will have, it's a different situation. So you have the different modes of vibration, and somehow you have one specific line which is called the zero phonon line, and the zero phonon line is this one. It's a line for which we have exactly the same frequency for the absorption and for the emission. Somehow, you do not see the lattice anymore. Okay? You have no interaction with the lattice overall. And then you have all the other lines that are associated to frequencies in which somehow you have that process. So somehow, there's a big difference between those lines. Somehow, if you compare to a single atom, like in vacuum, what you would have, for instance, if you are able to trap a single atom with an optical tweezer, using that, for instance, you have a two-level system. Okay? Where do I find my two-level system in solid-state physics? I only find it on the zero phonon line. So I can have coherent process between the absorption and the emission. It's only on the zero phonon line. Whereas, as soon as you go to other frequencies on the system, then somehow you have the interaction of the lattice, and the photon that will be emitted in the luminescence is not anymore coherent with the process of absorption. It has lost completely all the coherence due to the interaction with the lattice and the non-radiative decay. Okay? And so the question when you look to any solid-state emitter is, I would like to be as close as possible to a real atom. And for that, we can, for instance, look to the NV centers. In the NV centers, when we are at room temperature, we have a broad emission, okay? And here, this is a zero phonon line at the wavelengths of 637 nanometers. And it's very weak. Only a few % of the emission is inside these two-level-like atomic transition. Okay? Now, of course, I can imagine that if I cool down the system, I will strengthen the zero phonon line, and it's actually what happens. You see that, for instance, if I am a temperature of about 2 Kelvin, now the emission is much higher in the zero phonon line compared to the one that I can observe at room temperature. So this is a sign that somehow all these systems are less populated, of course. So you strengthen this emission, this coherent absorption and emission process. But still, this is not very good. What you would like is to be as close as possible as unity for the efficiency of for the light emission. And this is called the Debye-Waller factor. The Debye-Waller factor is a proportion of light which is emitted in the zero phonon line compared to the emission for all wavelengths over the full spectrum. And in the case of the NV center, even to the lowest temperature you can reach, a few kelvins, the Debye-Waller factor will be around 20%. So it means that you will not get enough photons concentrated on the zero phonon line. And after that, you need to filter them, for instance, to separate them from the background, which is associated to the broad luminescence that you have here. So this cannot be done very efficiently. So somehow, the NV center is a very efficient single photon emitter at room temperature, but it cannot produce perfectly indistinguishable single photons, and maybe I will come back to that during the lectures on Friday. Okay, concentrating perhaps on more the photon emission. Is it right? Okay, yes.
Could you please comment on, there are some features on the emission spectrum?
This, you mean this?
Yeah,
Yes, so this is the replica of the zero phonon line with one phonon of the matrix. But the phonon are broad. So basically, diamond has a typical phonon that you see, that you can measure, a very strong phonon Raman spectrum because it's very stiff, the diamond. So Raman, it's something where you see a very, very huge Raman line on diamond due to the fact that the stiffness of the diamond induced that. And basically, these are replica of the zero phonon line. So this is the ZPL plus one replica, and you can see that it broadens. Okay, it broadens due to the fact that somehow the strength of the interaction, of the coherent interaction, decreases significantly. But this can be perfectly explained by what happens by ab initio calculation and taking into account the interaction with the lattice. So all this has been remarkably modeled, and now we are doing this kind of experiment now, where we investigated that, what did change with pressure, for instance. If we apply huge pressure, huge strain on the NV centers, how are those spectrum modified? But people that do ab initio calculation can compute almost everything.
One more question. In the emission and absorption spectrum, they do asymmetric.
Mm-hmm.
In a perfect summation, it should be like symmetric, right? With a homogeneous broadening or inhomogeneous broadening. In both the cases,
but basically, yes, you're right, but basically, you have to combine with the thermal distribution. So it's the thermal distribution that gives this asymmetry. Just the thermal population of the different states. If there is, yes, please?
We look for a line on the emission spectra for temperature 300 and 200 to 200. So the wavelength has some temperature dependency for a single photons, or it's a
Yes, there is a shift, of course, because somehow let me see, temperature different. I don't know. I don't know. I guess so, but I don't know. I don't have the answer. What we've done is different experiments where we apply really pressure on the NV centers. So it's like the box that you see it, but now you make it smaller and smaller. So of course the energy difference will increase. So it's a little bit this kind of idea. And you want to understand how the physics of the system is modified. And this is much stronger effect than what temperature can do. Temperature is more like temperature won't change the potential well, okay? It will only modify the relative population and the decay and the interaction, the efficiency of the interaction with the lattice. So it's different things.
it's related to the thermal strain as well, because when you are changing the temperature, we have seen a previously medicine the size when you have some effect, the size of the tube will change. So that temperature also has some effect on that, and because of that there is some shift.
Can you repeat the question?
So I was just thinking, because of the temperature difference, there will be some thermal strain that is coming into the system.
Thermal strain.
Yeah.
Strain induce. Yes, yes.
And that is correlated to the change in some tube and another change in the membrane. That's
Yeah, the crystal will, the parameters will change like what we have. But again, yes, maybe we'll see that on the D parameter on the emission. It's more so. Yes, you're right. Okay, I understand the point now. Indeed, you can think about using these properties for measuring, for instance, the temperature. And but this is not, since the lines are rather broad, this is not very efficient. You need to pinpoint something a little bit like that. First, if I want to play with the expansion or contraction of the lattice, that will gonna work between something like 100 Kelvin and 300 Kelvin. It's where you have the highest modification of the crystal. Once you're below 100 Kelvin, everything is done. Everything is somehow frozen after that. So the changes are very, very tiny. But nevertheless, if you want, for instance, to use it as a kind of thermometer around 300 Kelvin, that's a good possibility. So then you can change a little bit and detect the wavelengths and see, for instance, just the intensity will be modified, okay? Or the spectrum is going to be modified. And you put that in a spectrograph and you try to see that. The NV center is not very good for that because it's too broad. But there are other defects, like the silicon vacancy center, that have narrower line, even at room temperature. And in that case, you can play with that. So there are indeed people that have used the silicon vacancy centers in nanodiamond as practical thermometers, following exactly your ID. Yes, you're definitely right. But the NV is not so good. But we will have another way to measure temperature with the NV centers, as you will see. Okay, now maybe something, I had a few questions about that. Can we go to the level of single emitters? And actually, if you want to detect single emitters in the solid state, what you will use to remove the background, it's what is called the confocal microscope. So a confocal microscope, it's something that was invented for biology. But in our case, it's a very simple system. It's just a system where I take the light emitted by a part of the sample, and I focus it onto a pinhole. And somehow, when I do that, I remove all the background by just this spatial filtering, all the background coming from the emitted by places other than a volume of a few micrometer cube around the focusing point of the microscope. So it's a way somehow to spatially filter the light. And once you have done that, you can really now detect a single emitter, an efficient single emitter that will produce photons at a rate of something like 10 to 20 nanosecond rate for the decay time. Then you can detect it. With a very good signal to background ratio, depending, of course, of the parameter of the lattice, nevertheless. And this is, for instance, what the detection, the spectrum for a single NV center that is obtained like that. And how can you check that it is a single emitter? Then what you do is you do an experiment which is called a single photon detection experiment, or Hanbury-Brown and Twist detection scheme. So what you do is that the photon comes here, and there is a beam splitter, 50-50% beam splitter. And the photon, since it's a single, you cannot cut in photon in two, it will have to choose this path, either being reflected or being transmitted. And then you have two detectors here, and you just check that if we have a single emitter, it will produce single photons, okay? And the single photons will induce no correlation between the click here. So I look to correlation between the two detectors. So I see, and then I just need to check if there is a click here, the absence of a click here, of a click on the other detector, and vice versa. And this is done with a correlator measurement that is just electronic box that somehow register all the counts and check now and measure the coincidence between the counts. And this corresponds, after normalization, to the definition of what's called the G2 function. And the G2 function is the correlation defined as a correlation between two detection events taking place at time t1 and t2. And since we are investigating a stationary process, the origin of time is not independent. The only relevant parameter is the difference of T1 between T1 and T2, so time tau defined as T2 minus T1. And then what I will do is now the measure define the G2 function as the probability of getting one photon at times T1 and another photons at time T1 plus 2, okay? And then I normalize it by the probability of getting one photon at time T1, one photon at time T2, which is, since we are within a stationary emission process, is simply the probability of getting photon at the average intensity that is emitted. Okay? So how can I do that? Then I can, to do the calculation, I can see that now I can express this as a conditional property. The conditional property is defined by the probability to detect a photon at time t plus 2, knowing that I have already detected the photons at time t. Okay, and this is the conditional property, probability. And then this is defined only, this is a one photon probability, but conditional one. And then this is only as now to be normalized by the probability of detecting one photon, which is here the mean intensity, the average intensity emitted by the emitter. Okay? So you have a very simple way now to measure that. Using all your clicks, you can evaluate this conditional property. It's not difficult. And you just now also detect the counting rate, and you have the experiment. Okay? And basically, you can show that this is something, at least the G2 at 0 is the number of coincidence click that you have divided by the number of click on one detector, the number of click on the other detectors times the duration of your measurement, T. Okay? And so basically, you measure that, and then you put different channels, and you have now, you can measure G at T, at G, change the time tau on which you do the measurement. Okay? And when you plot that for a single NV centers, so if I do now the computation for two-level emitters, I can do a very simple two-level model just using rate equation. I pump the system with this pumping rate R here, okay? And then the system will spontaneously decay from E to G. And of course, if I pump the system very strongly, the system will spend all this time, so I expect to get single photon, but at very, very high rate. Okay? So basically, now, when you do that, the formula is something like that. G2 over 2 is simply the probability of being in the excited state at time tau, knowing that you are at time t equals 0, the initial time, in the ground state. Okay? And then when you do the calculation, you have this simple, and you normalize by the average population on the excited state, and you have this very simple formula for G2 over 2. So you expect something like that. This is 1. 1 is just the shot noise level. And then as a function of tau. And then you have a drop here. And the drop here will be narrower and narrower if I increase R. And if R is much smaller than gamma, then I simply have an exponential minus gamma tau, which is just the decay of the excited level. Okay? Now, when I do that, when I do the experiment, this is what I observe. I observe something which is not exactly like that. I observed something which is higher than 1, close to the peak here. I first observed a value which goes almost to 0, okay, and which tell me that indeed I have a single emitter. And you can have a kind of, you can convince yourself that there's a kind of threshold around 0.5. Being below 0.5 tell you that indeed you have a single emitter, provided also that there be some kind of imperfection in the experiment, can be random photons coming from the background, will be associated to Poissonian statistics and not to this antibunching effect, because they are randomly produced. It can also be the time response of the detector that will somehow convolute the peak that I have here with this time response. And all that has to be taken into account. But as soon as you are below 0.5, you're sure that somehow you have a single emitter. But then, as you see here, the curve, there is all this part here, and this is a kind of bunching effect. It tells us that somehow the photons here appear at this time scale of about 100 nanoseconds bunched together. And this I will have to understand. I will try to see this as an exercise. Okay? So just to explain a little bit what we have been doing. Now, one thing I can do, and maybe this is once you have that, you have a very efficient single photon source that can be used to produce triggered single photon source. Now, what I simply need to do here is to use a chopped pulse intensity with a duration delta t pulse, okay, that are much smaller than the lifetime 1 over gamma. Okay? And with this, I trigger the emission. I put the system on the excited state, and just I need to wait the time it falls down to the ground state, and I got single photon emission like that. triggered synchronous with my pulse excitation of the system. So once you have this system, you can build a very efficient single photon source. Okay, and this is what we have done in the past. And I try, maybe I will have time to explain a little bit those experiments. Okay. So now, with all that in mind, we can really apply all these knowledge somehow, all these ideas perhaps more, to the NV centers. So there will be a lot of steps, and we try to go slowly in all these steps. We will start by constructing the electronic wave function. So somehow it's like the potential that we've done for the F centers, for the Farben center, but with the appropriate symmetry of the defect. Then once we have that, we will have the spin on top of that, okay? And since we have 2 electrons, we will have to play with the spin structure. So somehow this will be closed to the helium atom. And once we have that, we'll now focus onto the ground state Hamiltonian and see why we can detect optically the magnetic resonance, why we can optically polarize the system, and when we can optically detect the magnetic resonance. And then after that, tomorrow will be devoted to sensing. Okay? So I think for today, this will be already a good program. Let's continue a little bit. I don't know. So this is an image by a colleague in Saclay that is doing a lot of video on quantum systems. I think they are all in French, unfortunately, but if you can watch, this is a video by Julien Bobroff that he plays and explains what is a quantum, what is an NV centers, and you have here NV centers where it looks through the vacancy. Okay, he has a lot of jokes like that, but he's doing very nice work about for toward the public, explaining quantum technologies. Okay, so electronic structure of the NV center. We have the ideal structure of diamond. We know that it's sp3 bonding, okay, in the crystal structure, cubic face centered. So basically, we have the carbon here. That's our carbon here. The carbon will become a vacancy, okay, and it's linked by sp3 covalent bond to 3 carbon atoms. 4 carbon atoms, sorry. Okay, that's the structure of the diamond that we show like that, for instance. Tac, tac, tac. Okay? So now, and it's the idea that I explained from the very beginning, I will construct the defect from the dangling bond that are created by the vacancy, that are opened somehow by the vacancy. So I remove these carbon atoms. Now the carbon atoms becomes that vacancy, okay? So it leaves 3 bonds here. And here now, the carbon atom here is replaced by this nitrogen atom, okay? And the nitrogen atoms will have also the different bounding, okay? Because it has another electronegativity than the carbon atom. It has a higher electronegativity, so somehow it will attract more the electrons toward him compared to the carbon, okay? So now I want to compute the 1 electron wave function for the Coulomb interaction between the electron and the nuclei of the center. So this is this expression. So I take into account I suppose I have 1 electron in this system, okay, and I let it interact with the 4 system that I have here, okay, the 4 nuclei, nitrogen, carbon, and 3 carbon that I have here. So then, of course, what I will do is reduce my problem to a subspace where somehow I will only take it like what you do with molecules, that I rely on these dangling bonds. So again, I have 3 dangling bonds coming, so I combine, like in molecule, you've learned that I combine, for instance, the wave function of H2 molecules are obtained by linear combination of the hydrogen wave function. It's the same idea. Okay, I will use combination of that, and then I will just need after that that will be the basis of my system, and then I compute the system here. Okay, this potential within this basis. Exactly the approach that is followed for molecular physics. Okay, so I work now in an Hilbert. I don't take into account all the atoms. I don't know how to do it. Other people know how to do it by other technique, but I restrict myself to a Hilbert space of dimension 4, which is associated to the four to these orbitals. And now I just need to compute the Hamiltonian, the matrix element for for this nuclear potential. Okay, and once I have done that, I can look for the eigenstate and eigenvalues, and then I will have solved my problem somehow. At least for the ground state. Okay. So if I do that, you see that basically I have three type of parameter, four type of parameter. That parameter is a coupling between sigma 1 and sigma 1, okay, with the nuclear potential, or sigma 2 and sigma 2 and sigma 2, and sigma 3 and sigma 3. So basically, it's how the nuclear potential modifies the interaction between the vacancy and this system. Now I have this. This is a cross term that somehow describes this cross interaction. And then also I have this in the other interaction here, coming from here to here. This is this term. Okay? And I have another one, which is now this interaction here. I can do all that. So I have a 4x4 matrix. If I'm able to compute all these numerically, all these matrix elements, I can do brute force calculation, determine the eigenvalues, eigenstate. We can try that. That's not the right way to do. The right way to do is now to introduce the symmetry of the defect. That's what molecular physicists know how to do. They don't do that. They now change the basis. So they will use linear combination of the first basis, of the initial basis, that now fulfill the symmetry of the defect. And the symmetry of the defect, it's what's called the trigonal symmetry, C3V. So Z, we take it a line on the NV axis by definition, and X, we define it by the projection of one NV onto the plane normal to Z. To Z. One vacancy carbon atom can be random, okay? Because all three directions are equivalent. So I choose one like that. And that gives me my plane. And now the symmetry C3V is, for instance, you have a mirror symmetry and a 2 pi over 3 symmetry of rotation. Okay? Mirror symmetry along the Z plane, okay? And you have also the 2 pi over 3 rotation, you remain equivalent. So that's basically the C3V symmetry. Now, what I will do, taking into account that, I will use linear combination of sigma 1, sigma 2, sigma 3, sigma 4 to define a new set of orbitals that have this intrinsic symmetry. And then my guess is that then the 4x4 matrix should have then a much simpler form. And people know how to do that. What you do is that from group theory, you immediately know the good combination of the set of orbitals somehow that need to be used. That's group theory. Okay, you take a book explaining group theory, you read it, and then you know how to do it. So not so interesting for us. I give you just the result. And the result, you see this symmetry of 2 pi over 3, and this also the mirror symmetry. Basically, there's one function, I do nothing on it. It's the sigma n orbital. So the orbital that is localized on the nitrogen atom. This I don't touch. It will be like the identity. And the other one, you see, for instance, it's a linear combination of sigma 1, sigma 2, and sigma 3. So there is one which is the highest symmetrical system. It's 1 over square root of 3 for the normalization, sigma 1 plus sigma 2 plus sigma 3. And you see here, I have somehow put the distribution of the probability, the modulus square of the wave function on the plane, not modulus square, with plus and depending on the sign. And what I see is that basically you see the 2 pi over 3 symmetry when I do that. This is 2 pi over 3. And you see also the mirror symmetry when I am here. Okay? So it's a mirror symmetry that we have here. But this is symmetrical. Okay? Now I can do two other combination here and here. So you see that here the system will be mostly localized from here on the y direction, whereas here it will be mostly localized on the x direction. Okay? So somehow, again, this kind of, to go from the previous step to this one, you need just to apply the group theory. There's a lot of books that describe them. But now we can use these orbitals to compute the eigenstate for the Coulomb interaction that describe the electron and the nuclei of the center. And now this Coulomb interaction will have a simpler form. Okay? You see this was my initial 4x4 matrix. It was rather complicated. And at the end, it's much simpler. I have something which is restricted to this and this, okay? And another thing which is restricted, another subspace, or a 2x2 matrix, which is restricted to those states. Okay, so I have simplified my problem. And now they are they are diagonal. So I know already from that somehow phi2 and phi3 will be eigenstate of my system with the energy. They will be degenerate with the energy V minus minus. And this I can expect. X and Y somehow are equivalent direction in the system. And then there is another subspace in which I will have to diagonalize this matrix, and that will give me the other eigenvalues, eigenenergy, and eigenstate associated to the system. And this is just the combination of that. So it's a dangling bond coming from that, and a distribution of electronic density on this plane. Okay? And they interact. So I have completely simplified the system. At least you can do the calculation. You put that in ChatGPT, in Mathematica, in whatever you want, and give you the result of the calculation. They are not very difficult to do. But what is mostly important is that I will have A'1, A1. So I will come back to this denomination, which are rather strange to use compared to atomic physics. But basically, they are linked to the symmetry, to the choice of symmetry of the system. But then we have this, and this. Okay? So we have now 4 orbitals that are eigenstate of the nuclear potential. Okay? And with the corresponding energy. I do not know very well, at that stage, I do not know how to order them. This is the important problem. So I've been able to take into account, so I am at that step, okay? This is my step now. I started from the symmetry of the defect. I took into account the symmetry of the defect to deduce the set of orbitals that needs to be used. I use this set of orbitals to compute, to evaluate the interaction of the electron-nuclear system. That gives me the eigenvalues and eigenstate somehow. And now I have to order the state. What is the ground state and what are the state above? And usually, the rule, again, is that the most symmetrical state, that will be A prime 1, that state, okay? This is the most symmetrical one, will have the lowest energy. And this, of course, if you want to do it carefully, you need to confirm your calculation. This is just a guide somehow. And at one point, you need ab initio calculation. And this ab initio calculation will indeed indicate what level, the energy levels. But it will also allow you to do something that we are not able to do with this approach, is to determine where the levels are with respect to the conduction band or the valence band. And actually, we found in the ground for the NV centers that the lowest energy state is within the valence band, whereas the other one appear within the band gap of the diamond, which is 5 electron volt. Okay? So once we have done that, we have this set of systems. So basically, we have now four states, and we need to fill them with the electrons. So now I am at that step, okay? So you've seen step 1. That was step 2. That is step 3. And then we fill them. So this produces this. This is the important point. And now we have to go to step 6. Step 6 is fill the state. Okay? And remind, we have for the NV minus center 6 electrons. Okay? Okay, those 6 electrons will occupy the single electron orbitals from lowest to highest energy levels, following Hund's rule. It's the Pauli principle. I can put 2 electrons, since they are fermions, but with opposite spins, or in the associated singlet state, and we'll come back to that. So I fill the state. 1 here, 1 here. These electrons are in the valence band. They are somehow bounded to the full crystal. I don't care about them. They cannot interact now anymore. They are forgotten. And then there is, then there is 2 electrons on A1, and then 1 electron on AX and 1 electron of AY on these systems. Or equivalently, I have filled orbitals and two holes in these energy levels. And now the first excited level will be to take 1 electron from A1 and bring it to AX, okay? Or to AY at a given choice. And the second excited level will be to take the 2 electrons from A1 and bring them to AX and AY, which are, in which I have the space to put 1 electron. So I have very simple pictures of the distribution of electron in the state of the defects. But the picture is somehow oversimplified. We have neglected a few things. First, we neglected the spin-orbit interaction that split the spin-up and spin-down level, so that somehow they are no longer degenerate. You know that somehow the spin-orbit interaction will split that into different components. And if I want to do things more rigorously, I have to do a full quantum treatment, but again, this can be done by applying DFT techniques, for instance, and I will construct like that. I will build a many-body wave function on the system. But this is something beyond what I can do. I leave that to theoreticians, and we collaborate with them on the topic. Okay, just a quick reminder of the spin-orbit interaction. You can forget the calculation, but the spin-orbit interaction will be about, for the specific case of the NV centers, will be around 5 gigahertz. So this is at low temperature, so something weak. If you remember the spin-orbit interaction, for instance, for sodium, it's huge. And it creates the splitting, it's 6 angstrom, the splitting between the 2 D1 and D2 line of the system. In the NV centers, basically, and it's a specific feature of the NV centers, there's no reason for that, the splitting is very, very weak. So somehow, the the interaction, so let's put it like that. The electron going between these state that will produce the light absorption and emission cannot change the spin. The spin lives somehow in in a completely different Hilbert space, and there's no connection between them. It's what it tells, okay? So, and this is unique property. So somehow my system does not mix the electronic wave function and the spin wave function. They are decoupled. And that's a great feature, and most of the application will actually rely on this decoupling. And this is just by nature. There's no real explanation up to what I know about that property. There's still a little bit of mixing. I would like also to remind you that somehow we have in the excited state a Young-Taylor effect, like what we described for the electron in the box. So somehow this will induce an angular orbital averaging. There is a dynamical Young-Taylor effect in the excited state will remove all specificities associated to the different transitions that can have on the system. And this is also quite important, but maybe I will explain that later on. Yeah, perhaps I just do that. Yes, and then I will stop at that point. Okay, let's consider now the transition between the different systems. I can go from here to here. In this case, this will be the transition. The transition will be take that electron and put it, for instance, on AX, on the AX state. This will, the matrix element that can couple A1 to AX. A1 is something that is very symmetric. This is A1, okay? To this, it's an electric field that has to be aligned along the x-axis. Okay, so this is associated to a dipole or selection rule along the x-axis. And that now, this transition, where I go to the y branch, is associated to an electric dipole along the y direction. So I need now to put the polarization of excitation along that axis, and then I excite that. Of course, I may imagine that somehow there is a combination of all those transitions. But then what happens is that at least at ambient pressure, at ambient condition, ambient temperature, the Young-Taylor effect will somehow decouple that. Somehow you will have, because this is a kind of natural symmetry of the system. So there is a kind of dynamical effect which tells you that basically you will have a combination of this, for instance, and a combination of that, but they are completely incoherent. Okay? I cannot imagine, so for instance, if I put a polarization at 45 degrees, okay, I will not excite coherently a polarization that would be a linear combination of those states. I will have independent excitation of the dipole along X and the dipole along Y. And this is also, I will show you this. Just a little bit of crystallography. Now, if we take, for instance, a diamond, we have different cuts that are possible. And if I take, for instance, a 100 cut, then I will have 4 orientation of the NV centers that are oriented at 35 degrees with respect to the axis perpendicular to the 100 plane. I can also have a 111 cut of the diamond. And if I have a 111 cut, then one of the NV center will be oriented for taking into account a random ensemble, will be oriented like that, and the other sample will be oriented at the complementary angle to 35.27 degrees. And now, for instance, I can do this simple experiment to really show you that the emission, at least at ambient condition, is realized, is the contribution of these 2 independent dipoles. I take the laser, the excitation laser, and using a λ/2 plate, I turn the angle of the polarization. If I have a 111 sample For 111 sample, now it's independent. If I turn the polarization like that, okay, of my laser excitation, the projection on X and Y will be always the same. Okay? So I will not see any difference. So the intensity will remain constant. And it's actually what we observed. This is what is observed for 111 center. Now, if I look to other centers where they have now so their dipole will make an angle around that, you can easily imagine that when I will turn the polarization, I will be along mostly one direction, and then go toward the other direction, and et cetera, et cetera. So I will have a modulation, and the modulation is shown here. And basically, this modulation tells you which family you address between the three other families and the 111. Okay? So using this trick, I can really know which family of NV center I am addressing in my compound, just due to the fact that I have this feature of the NV, this orbital averaging effect that leads to emission along two dipoles. Okay? So this is important, okay, at that point. So we now understand here the main properties of light absorption and emission by the NV centers, taking into account these electron orbitals. Now, what I need to do is I have to take into account the spin. Okay? And the spin, that's another game. And we will do it this afternoon. Okay? So it's like what you did with a helium atom, perhaps in quantum mechanics calculation. You compute the energy level of the helium atom, and then you fill it by the two electrons, taking into account that you have to apply Pauli principle since electrons are fermions. So we'll do exactly the same here. I have my electronic my electronic orbitals, and we'll fill them with the two electrons that are left. Okay.
All right, so thank you very much.
And we see this afternoon.